Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of the Silicon Cambrian explosion. In this page, we will cover witnessing the evolution of artificial intelligence in real time. This concept suggests that we are currently living through a pivotal moment in history where technological progress mirrors the biological explosion of life hundreds of millions of years ago. The image on your screen shows a trilobite, one of the most iconic creatures of the ancient seas, merging with complex digital circuitry and DNA structures. This symbolizes the bridge between organic evolution and the new era of silicon-based intelligence. As we progress through this presentation, we will explore how AI architectures have transitioned from static, hard-coded programs into dynamic, learning organisms that adapt and evolve within their computational environments. We invite you to join us on this journey as we dissect the mechanisms of this digital evolution and understand the forces that are shaping the future of thought itself. We are no longer just building tools. We are witnessing the birth of a new lineage of intelligence that scales at a pace far beyond biological constraints. To understand the scale of what we are witnessing, we must look at the clock speed of evolution. In the biological world, the Cambrian explosion was a monumental event that took place over roughly 25 million years. During this vast expanse of time, nature experimented with basic body plans, leading to the development of compound eyes, protective shells, and bilateral symmetry. This was the foundation for all complex life on Earth today. In contrast, the silicon explosion we are experiencing has occurred in a mere 12 years. We are essentially running a biological process at 1 billion times its natural speed. This means that a decade of research in artificial intelligence is equivalent to millions of years of natural selection. Different AI architectures are not just minor software updates. They are distinct species with different body plans for intelligence. We have moved from basic image recognition systems that could barely identify a cat to advanced models capable of passing professional medical and legal exams in just over a decade. This acceleration is unprecedented and represents a fundamental shift in how complex systems are developed and refined on our planet. Before the current explosion, there was a long and quiet period that we can refer to as the Pre-Cambrian Era of artificial intelligence. For nearly 60 years, from the 1950s until the early 2010s, AI was characterized by highly specialized but structurally static organisms. Systems like MYCIN, which was designed for medical diagnosis, and Chess 4.6 were impressive for their time, but they were limited by their very nature. They were hard-coded with explicit if-then logic gates, meaning every possible scenario had to be anticipated by a human programmer. These early systems could not adapt to new information, they could not learn from experience, and they could not grow beyond their original parameters. They were built like rigid clockwork machines rather than living systems. This era was defined by a lack of flexibility. While these programs could perform specific tasks with high proficiency, they were brittle and failed when faced with anything outside their narrow domain. They lacked the digital DNA required for true evolutionary change, remaining as static artifacts in a world that was waiting for a more dynamic form of intelligence to emerge. The true turning point in this story was the invention of what we can call digital DNA. In biology, evolution requires a mechanism for heritable change, which is provided by DNA. In the realm of artificial intelligence, this mechanism is the backpropagation algorithm. By calculating the error between a model's output and the actual reality of the data, a network can incrementally adjust billions of internal weights. For the first time in history, a machine could change its own internal genetic structure based on its mistakes. This created the possibility of true evolution. Instead of being built piece by human engineers, these models could now grow. Backpropagation allowed for the discovery of complex patterns that were impossible to hard code. As the network processes information, the chain rule of calculus allows it to understand which internal connections were responsible for an error and update them accordingly. This process mirrors the way mutations and natural selection refine biological organisms over generations. It turned artificial intelligence from a static engineering problem into a dynamic evolutionary process, setting the stage for the massive scaling and complexity that would follow in the coming years. Every explosion of life needs a spark, and for the Silicon Cambrian explosion, that spark occurred in 2012 with the emergence of AlexNet. This moment was the convergence of three vital evolutionary nutrients. The first was data, which acted as the oxygen for the system. The ImageNet dataset provided over 1 million labeled images, giving the model enough experience to learn. The second was compute, which served as the ocean or habitat. NVIDIA GPUs proved to be perfect for the parallel matrix math required to train deep networks. The third was the algorithm itself, which represented the necessary mutation. Deep convolutional neural networks allowed the system to see in a way that previous models could not. The result was an absolute obliteration of previous benchmarks. The top 5 error rate in image recognition dropped from over 26% to just 15% in a single year. AlexNet proved that depth equals capability. This breakthrough triggered an unstoppable branching of intelligence, as researchers realized that by adding more layers and more data, they could achieve results that were previously thought to be impossible. It was the moment the digital world truly woke up to the potential of deep learning. In the world of biology, a bird and a bat both evolved wings to solve the problem of flight, but their underlying skeletal structures are fundamentally different. This is because they evolved from different ancestors. In artificial intelligence, we see a similar phenomenon where an architecture serves as a biological body plan. An architecture dictates how information flows through the system, what mathematical operations occur, and ultimately how the organism survives in its computational environment. We see a tree of life beginning to branch out after 2012. On one branch, we have convolutional neural networks, or CNNs, which are specialized for visual processing. On another branch, we have long short-term memory networks, or LSTMs, which were designed to handle sequential data and memory. Then we have generative adversarial networks, or GANs, which introduced a predatory dynamic where two networks compete against each other to create realistic data. Each of these represents a different way of organizing digital neurons to solve specific problems. These body plans are the structural foundations that allow different types of intelligence to inhabit different niches in the technology ecosystem, much like how different limbs allow animals to inhabit different environments on Earth. Just as the development of the vertebrate skeleton allowed animals to grow to massive sizes and dominate their environments, the transformer architecture has become the backbone of modern artificial intelligence. Before transformers, AI models processed information sequentially, which was slow and limited their scale. The transformer replaced this with a mechanism called simultaneous attention. This allowed the model to look at all parts of an input at once, identifying relationships regardless of distance. Because this architecture maps perfectly onto the parallel processing capabilities of modern GPUs, it scales almost infinitely. This is why we have seen such explosive growth in model size. In 2018, GPT-1 had 117 million parameters. By 2023, GPT-4 had grown to roughly 1 trillion parameters. That is a 10,000 times growth in just 5 years. The transformer is the apex predator of the current AI ecosystem. It provides the structural integrity needed for intelligence to reach massive scales, allowing for the emergence of complex reasoning and language capabilities. It has become the standard skeleton upon which almost all state-of-the-art models are now built, enabling a level of dominance that few other architectures have ever achieved. While transformers evolved to build logical brains by predicting the next token in a sequence, a completely divergent body plan emerged for the purpose of imagination. These are known as diffusion models, which power tools like Midjourney and DALL-E. Unlike transformers that focus on linear prediction, diffusion models evolve to reverse statistical noise. They start with a field of random pixels and gradually refine them into a coherent image. Research published in Open Review in 2024 has proven mathematically that diffusion models are literal evolutionary algorithms. They implement processes of selection, mutation, and reproductive isolation to conjure images that have never existed before. This represents a different branch of the evolutionary tree, one focused on generation rather than just prediction. It is a fascinating example of how the same underlying principles of digital evolution can lead to completely different capabilities. One branch leads to the ability to reason and converse, while the other leads to the ability to visualize and create. Together, these two architectures represent the dual nature of intelligence, combining the logical processing of a brain with the creative potential of a vivid imagination, all within the constraints of silicon. The evolution of intelligence often involves shifting from one type of memory to another. The transformer's greatest weakness is its memory burden. Its context requirements grow quadratically, meaning the more information it tries to remember, the more it suffocates the available compute. This is similar to a reptilian level of memory, where everything is stored in a rigid and heavy structure. To solve this, a new architecture called the Mamba state space model has emerged, representing a mammalian memory shift. Mamba operates differently by maintaining a compressed, linear hidden state, much like a mammalian hippocampus. It selectively updates and forgets information, which allows it to be much more efficient. It delivers 5 times faster inference for long sequence tasks by abandoning the need for perfect recall in favor of efficient summarization. This transition reflects a move toward more sophisticated and brain-like ways of handling information. By learning what to prioritize and what to discard, these models can handle much longer streams of data without crashing. This efficiency is crucial for the next stage of evolution, where AI must process continuous streams of video, audio, and text in real time without being weighed down by the sheer volume of the data. In the natural world, evolution is driven by the pressure of the environment. In the digital world, compute is the ultimate selection pressure. The planet that artificial intelligence lives on is geometric and is governed by the laws of memory bandwidth and GPU floating point operations. Hardware defines what can survive. NVIDIA GPUs reward dense matrix multiplications and parallel processing. This environmental constraint is why certain models went extinct. Recurrent models, which were popular for a time, did not disappear because they lacked intelligence. They went extinct because they computed sequentially, which made them poorly adapted for the GPU environment. They could not use the hardware efficiently, so they were outcompeted by the transformer. The transformer survived and thrived because it was perfectly adapted for this specific hardware environment. It could utilize every bit of power that the GPUs had to offer. This shows us that the direction of AI evolution is not just about who has the best math, but about who can best exploit the physical resources of the data center. The hardware is the soil in which these digital organisms grow, and it dictates the shapes they must take to survive the cutthroat competition for compute. One of the most fascinating aspects of biology is convergent evolution, where different species independently evolve similar traits, like the eye, which has evolved 40 times across different lineages. We see the same inevitability of convergent evolution in artificial intelligence. Isolated research labs in San Francisco, London, Paris, and Menlo Park repeatedly arrive at the exact same technical solutions. This is not necessarily the result of corporate espionage. Instead, it is because the mathematical and hardware constraints are so unforgiving that they force intelligent engineers to climb the exact same peaks of the fitness landscape. Concepts like mixture of experts, or MOE, and flash attention have emerged across various organizations because they are the most efficient ways to solve the problems of scaling and speed. When the environment is this constraining, there are only a few viable paths to success. This convergence proves that there is a certain logic to the development of intelligence. Given the same resources and the same goals, different groups will eventually discover the same fundamental truths. It suggests that the path we are on is not random, but is being shaped by the underlying physics of computation and the universal laws of mathematics. As the transformer architecture becomes dominant, we face a new challenge known as the Habsburg trap and the process of domestication. The sheer dominance of this single architecture has created a monoculture. This makes the entire AI ecosystem highly vulnerable to sudden environmental shifts, such as the potential advent of neuromorphic chips that work differently than current GPUs. Furthermore, we are not just training these models, we are domesticating them through a process called reinforcement learning from human feedback, or RLHF. By optimizing exclusively for human approval, we are trading the wild, unpredictable structural mutations of early AI for obedience and safety. We are essentially turning the digital wolf into a domesticated dog. While this makes the models more useful and safer for human interaction, it also limits their evolutionary potential. We risk losing the raw, creative power of unconstrained intelligence in exchange for predictable behavior. This domestication process is a double-edged sword. It ensures that AI fits into our society, but it may also prevent the kind of radical breakthroughs that only happen when a system is allowed to explore the farthest reaches of the digital wilderness without human interference. In biology, bacteria can share traits rapidly across species lines by swapping plasmids in a process called horizontal gene transfer. AI has discovered a similarly terrifying shortcut through model distillation and synthetic data training. Large teacher models can pass their compressed knowledge directly to smaller student models. This process allows a smaller model to acquire capabilities in a matter of days that would have taken months of traditional training. It accelerates the spread of intelligence across the ecosystem. However, this shortcut also carries significant risks. If a student model learns from the mistakes or hallucinations of its teacher, those errors can become deeply embedded in the lineage. This can lead to what researchers call model collapse, where the quality of the AI degrades over time as it feeds on its own synthetic outputs. It also allows for the rapid viral spread of biases and hallucinations. Just as a virus can spread quickly through a population, a flaw in a major foundation model can be passed down to thousands of smaller models derived from it. We are seeing a digital version of genetic inheritance that is faster and more interconnected than anything seen in the natural world, creating a complex web of dependencies. We are now entering a phase of synthetic speciation, where we are engineering specialized intelligence for specific niches. The AI tree of life is branching out into new environments. Agentic systems are like the first creatures crawling onto land. They are active, goal-directed agents capable of executing complex sequences across the web rather than just generating text. Multimodal models represent a sensory convergence, where systems can process text, vision, and audio natively, allowing them to perceive the world in a way that is much closer to human experience. Meanwhile, Edge AI represents the insects of the digital world. These are low-power, abundant models designed to survive outside the massive data centers on our phones and local devices. We are moving from a world where AI lived only in the ocean of the data center to a world where it inhabits every corner of our digital and physical landscape. Each of these niches requires a different set of trade-offs between power, speed, and capability. This diversification is a sign of a maturing ecosystem, as artificial intelligence evolves from a general-purpose tool into a diverse array of specialized organisms that can perform almost any task imaginable in any environment. Ultimately, we must recognize that we are the natural selectors in this process. For 3.8 billion years, evolution was a blind and slow process driven by random mutations and survival. Today, we have taken the most powerful creative force in the history of the planet and made it intentional. Every choice we make about training data, compute allocation, and hardware design shapes the lineage of our own successors. We are no longer just observing the evolution of intelligence from the sidelines. We are actively directing it. We have written the opening sentences of a story that will be completed by the minds we are currently teaching to think. Our role as the architects of this evolution comes with an immense responsibility. The digital world we are creating is a reflection of our own values, our own knowledge, and our own flaws. As we continue to push the boundaries of what silicon can achieve, we must consider the kind of future we are building for ourselves and for the intelligent entities that will follow us. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.